that's a whole nother topic. So why don't we get started here? I'd like to welcome everybody. I can't see faces, but we've got a little over 40 participants. Welcome to, on behalf of Olympic Climate Action, to our special program. We're really, really honored to have Andrew Fountain here. A little bit on Olympic Climate Action. We're a group of local concerned citizens here, grassroots group seeking a kind of a safe and prosperous and sustainable future on the Olympic Peninsula by raising awareness of and addressing and trying to take action on climate change. If you're interested in joining us, if you're not a member, see our website. There's ways to join up and find out some of the things we've been doing over the years. We're always looking for folks. As I think we all know, it's a pretty pressing topic that concerns all of us. And tonight's program is indicative of that. I wanted to share one anecdote before we dive in, and that is I've worked here on the peninsula, recently retired from the park, but I've been here for 40 years. And when I first got to the Olympic Peninsula, I had the honor of climbing Mount Anderson, climbing up to Anderson Pass and going up to the moraine and going around the lake and up onto the glacier, climbing up to Flypaper Pass. You know, we were in crampons and ice axe and roped up because we were crossing the Anderson Glacier to get up to the summit. And in my career, during my career here, the Anderson Glacier is no more. It's gone. And I sometimes joke that I don't feel geologically old, but when I see that kind of thing, I do. And we're going to learn a little bit more about why that's happening and sort of the measuring of that. And Dr. Fountain's going to do that. He tells me that he was a nerdy kid, and that he was always interested in ice, that he used to go out and catch snowflakes and preserve them. I'm not really sure how you did that, but he went from that into getting his PhD at the University of Washington and working for the U.S. Geological Survey on glaciers, studying glaciers and the impacts of climate on them all around the world, including the Glaciers of the West website, if anybody's ever looked at that. And he's been at Portland State University doing research on glaciers since the mid-90s. So he's got decades and decades of research, and we're really honored that you're willing to share your expertise and the results of the recent paper with us this evening. A few housekeeping things. We're going to probably spend 45 minutes or so on the program, and then we'll have plenty of time for the Q&A afterward. And I think everybody is muted right now, but we will unmute folks at the end and take questions. And I'll keep an eye on the chat, but you'll be able to ask your questions in person afterwards. So why don't we plan on that? So I think that's all the housekeeping, and we are recording. If you know folks that wanted to see this program but had other obligations, we should be able to post this eventually on the Olympic Climate Action website. So thanks everybody for joining us, and Dr. Fountain, it's the screen and everything is yours.
Well, thank you, Janice, and it's good to be here virtually. I am in my house, so it's good to be here too. I just wanted to say thanks for everybody for organizing this, the Olympic Climate Action Group. And the topic is certainly prescient in your backyard. And this is just as a little background, this is part of a larger study we're doing across the Western US, trying to figure out how these glaciers are reacting to climate warming and what their ultimate fate might be and how long that might take. And we're starting with the Olympics for a lot of reasons that you'll see forthcoming. So, you know, the Olympic Peninsula has a long history of glacier observations. As a matter of fact, it was one of the first areas identified back in the 1950s as a site for monitoring glaciers. here on the left-hand side, this is Blue Glacier, an IGY glacier. What that means is International Geophysical Year, where they had global glacier observations, global aurora observations, global earthquake observations, try to get a sense of what geologic and physical activity there is on Earth, and what are the global connections. And glaciers was one of those topics. And here you can see on the map on the left, they had identified glaciers up here in Alaska, and then the only one they identified down here in the lower 48 is Blue Glacier. You know, one could argue that the rise of modern glaciology in America started at the Blue Glacier. In 1955, a professor from the University of Washington, Dick Hubhley, initiated a program on the Blue Glacier to study how the weather and governs the rate of melt, as well as the rate of snow accumulation. And by that point, there had actually been very few studies on this, like what exactly controls melt. Is it just warm temperatures, or does high wind speed also matter? And so he initiated some of the original studies. And then soon after, Caltech from down in California had a whole project on the Blue Glacier for more than 10 years. And the list of people here that probably don't mean anything to you, for those of us in the glaciological community, these are the fathers of modern glaciology, in some respects globally, but certainly within the US. And one of the things they did was Barclay Cam here drilled an ice tunnel, I should say cut an ice tunnel in the side of the glacier in order to measure the movement and how the glacier moves at and near the base of the ice, a subject that was not well understood. What you see here on the right is a photograph of Blue Glacier itself and one of Bill Fairchild's airplanes that they used to land on the glacier, drop off the scientists and equipment, and then take off, dive off the ice fall, hopefully gaining enough airspeed that they can continue back to their airfield by Lake Union in Seattle. So the Blue Glacier was the proving ground for a lot of ways we do things today, how we study glaciers, how do we drill into a glacier? What about taking a small camera and lowering it in a borehole and measuring, or I should say, viewing what the inside of the ice looks like, and so on and so forth. All that happened on the Blue Glacier. And let me just show you a couple of pictures of this. This is one of Ed LaChapelle's meteorological towers, a tall one, and a little one here to study how the snow melts based on the weather conditions. And this here on the far right is the ice tunnel that they dug. And you can see here on these smaller photographs, they are roped up, belaying themselves down to the ice tunnel in order to dig into the ice tunnel using electric jackhammers, among other things. It's cold, wet work for sure. One experiment that is still going on are these triangles here. These are twisted steel triangles, twisted in a way that it's unambiguous that is something intentional. Ed LaChapelle had distributed these across the snow surface, labeling each one in the hopes that people decades later will find them, locate where they found them, and they would have, from that, they know the original position, they know where they find it, and then they know something about the travel time through the ice, as well as the direction of the ice motion. Offhand, I don't know if anybody's found any of these, but it's maybe an experiment still ongoing. So I just wanted to illustrate that and just review briefly review the history to let you know that Blue Glacier and the glaciers of the Olympics are not some faraway place that has largely been ignored by the scientific community. It's been an area of episodic research since the turn of the last century. And today, even today, it's mostly from the University of Washington, who has small field studies on the glacier today. So back to what I've been doing, what we've been doing, and that is we've been trying to understand how the glaciers of the Olympics have changed in the past, as well as what might happen to them in the future. And the first thing to think about is, what is the climate of the Olympic Peninsula? Well, you can see this graph here on the left. The bars here are precipitation, and the axis for precipitation is here. And this comes as no surprise, I'm sure, to anybody listening to this, that wintertime is the time you get all the snowfall, and in the summertime, there's hardly any precipitation whatsoever. And of course, it's warmest in the summer and coldest in the winter. This is the maximum and the minimum, and this is the average here. But the key point is, and how this differs from a lot of glacier covered areas, is look at the winter temperature here. It's very warm. It's very close to freezing. You know, the average monthly temperature is no more than about -2 or -3 degrees below sea, or below freezing. So unlike other areas where it might be -10 or -20, here in the Olympics, you're very close to the freezing temperature in winter. And that becomes quite important to the story. On the right-hand side, you see this colorful map. This is done by Ann Nolan and Chris Daly at Oregon State. And what they've done is they've mapped what they call the temperature, the winter temperature of snowpacks, and looked at what they call the snowpacks at risk, those snowpacks close to the melting temperature. So you can see here in far Montana, it's very cold snow. And then as you get closer and closer to the coast, here in the Cascade Range in Washington and Oregon, it's cold snow, but not quite as cold snow. And then as you get on the margins of these areas, as well as the Olympics, you see warm snow and high precipitation. So in other words, lots of snow, and it's all pretty warm. So in a global warming situation, the places that are colored orange here would be the first to lose their snow cover. And a lot of that, you can see, is here in the Olympic Peninsula. And that's because the Olympics are so close to the ocean, and the mild weather, the winters don't get quite as cold. So with any climate warming, that snowpack is at risk of not forming. And I'll come back to that later. So just to give you kind of a thumbnail sketch, looking at the topographic characteristics of the glaciers in the Olympics. This is based on the work of Rich Spicer, who did his master's thesis back here in the 1980s. And he compiled a lot of the areas, and we looked at the elevations and topographic characteristics. And you can see here that a lot of the glaciers are really quite small, about 0.1 square kilometers. So, you know, you only have a very few big glaciers up here. You know, a square mile is up here someplace. And glaciers don't really get much larger than 6 square kilometers. So this is typical of a lot of places, or most places in the US, that we tend to have lots of little glaciers and not many big glaciers. Another salient feature here is the elevation. Look at this. Most of the glaciers are at about 1,700 meters. So that's well less than 6,000 feet. That's closer to 5,000 feet. Again, that's unusual. Even in the North Cascades of Washington, they're up around 7,000 feet. And then if you go down to California, you're up to 10,000, 11,000, 12,000 feet. So these are very low elevation glaciers. And of course, like most glaciers in the Northern Hemisphere, they face north because it's more shaded from the sun that way, which suggests that these glaciers are already affected by the local climate, that they need a north-facing slope to exist. South-facing slopes, they get way too much solar radiation from the sun and enhance the melt, and they would shrink quite rapidly. This is not true so much in Antarctica or Greenland, where the temperatures are so cold, it doesn't matter which direction glaciers face. So what we did, we started with Spicer's information, and which included glacier areas. He mapped all the glacier areas back in the day when pencils and paper maps were used. And we redid that using digital methods and using GIS and satellite imagery, as well as some aerial imagery. And what you see here on the left, these are both the Eel Glacier, taken with aerial photographs in 2015. And you can see this is what you would see on the aerial image. And then basically we go in using the geographic information system and outline the glaciers. So we've done this for a number of aerial photo flights, as well as satellite coverages over the years, to compile how the glaciers have changed in area over time. One thing, and this is more of an aside that I wanted to mention, is take a look here. Up here, you see that line there? That's a moraine. That's a kind of a deposit of rock material that the glaciers deposit on the lower edge of the glaciers. In the next picture, I'm going to show you an expanded version of this. This is still the Eel Glacier. And here's this moraine. And you can sort of trace the moraine all the way through here. And it's less clear here, but if you're able to zoom in, you'd see it come through here. And I've kind of made a dashed line here. Well, we know that this moraine was formed during the Little Ice Age, which nominally ended in the Western US around 1850. So even though we don't have instrument records or photographs of these glaciers back at that time, from this recent geologic evidence, we can estimate where the glaciers were back, almost 200 years ago. So I just want to kind of illustrate some of the things that we can use on the landscape to push the record back, but that's not germane to this talk, but I just wanted to give you that little background. So, so what have we seen? So we've had good aerial imagery and satellite imagery for these 4 years. And this is from the early 1980s to 2015. And you might think, well, wait a minute, why not more places? Why not more times? Why just these 4? Well, the problem is that the imagery isn't always taken at the right time. You can have snow cover that covering the entire landscape or large parts of the landscape, and you don't see the glaciers because everything's snow covered. And of course, weather, clouds, for example. And we all know that the Olympic Peninsula is really cloudy. So it kind of takes a unique set of circumstances, which is clear weather, and it's got to be late summer when the snowpack is at the minimum and we can see the glacier outlines the best without interference of the snow cover. So for the Olympics, then there's really only 4 years in which we had good imagery. And then at each one of those years, we outlined all the glaciers and developed this kind of population map. So this is the area down here, again, in square kilometers. It's a funny scale here because it's a logarithmic scale, not your normal linear scale. That's the way we can kind of pack it together, kind of, so you can see what the trends are a little bit easier than if we used a regular normal linear scale here. And by the way, this 0.01 here, square kilometers, that's incredibly small. That's basically a football field by a football field in area. So you're talking about very small glaciers. So you can see here that with time, the population of glaciers are getting smaller, and the distribution of areas are becoming more and more skewed for smaller areas. And this is what's seen elsewhere in the world. This is on the right here is just kind of a table of values. I won't go through any of this other than to say that between 1981 and 2015, almost half of the glacier area has been lost. And we can estimate volume by knowing the old topography from the USGS topographic maps. So we know the elevations of what the glaciers used to be. And then a LiDAR survey, where it's an aircraft with a laser beam that they can estimate the elevation or measure the elevation of the land surface. They flew the Olympics for a completely different reason, looking at snowpack thickness across the region. But we were able to use that for glacier elevation. And by subtracting the elevation in 2015 from the elevation back in the 80s, we come up with a elevation change, and from that a volume difference. And that's what these values are here on the right-hand side. So there used to be about 1.5 cubic kilometers of ice, and again, that's now down to about half, about 0.75 cubic kilometers. And that's equivalent to losing about 16 meters off every glacier. So you shave this, on average, 16 meters off every glacier. So what's that? That's about 50 feet of ice that you shave off from all the glaciers, to kind of give you a more intuitive sense of the kind of change that we've seen. This is a plot of elevation on the left, and on the x-axis, it's fractional area change. Rather than just do area change, like, the glacier shrunk from 1 square mile to half square mile. The problem is little glaciers don't shrink as much because they're little, and big glaciers kind of shrink a lot because they're big. So maybe a 1% change of a big glacier might be, just for sake of the story, might be a loss of 1,000, 1,000 square meters, whereas a small glacier that's only a 1,000 square meters, that might only lose 5 square meters. So you can't really compare those two, because little changes on big glaciers don't compare to little changes on little glaciers very well. So what we have to do is we do it in terms of fraction or percent. This is another way to think about it. So it's minus 100% down there. There's 50% loss, and then 0% loss. And that's a way to take out the area of the glacier, remove the area of the glacier from biasing the data. So you can see here, basically, that lower elevation glaciers lose more area than high elevation glaciers. And that makes sense, right? Because as the climate warms up, the lower elevations are going to be warmer and above 0 degrees centigrade, creating more melt than higher elevation glaciers, which are much cooler below freezing and don't warm up as much beyond the freezing threshold. But take a look at this again. Forget this black line. There's a lot of scatter in this data. I mean, look at this. At 1,600 meters, you can have everything from complete loss to only 10% loss. So what accounts for this, the scatter in all this data? Well, this is where topographic influences become important, particularly for small glaciers. Here's an unnamed glacier here, and this is just examples of it. These aren't actually these glaciers. This is just the idea of how this changes. You can see this glacier here is sitting in this bowl surrounded by these mountain peaks. And you can imagine that as the snow falls, it accumulates on the side. These valley walls then avalanche, and the snow then accumulates down here on the glacier. So this glacier gets not only the direct snowfall, but contribution from avalanches. So that's getting more snow than it would otherwise. So over time, it would tend to shrink less because it's getting tons of snow. Correspondingly, here's a glacier sitting on a very flat, it's inclined, but a fairly flat mountaintop. And there is no or very little avalanching from the sides. So under the same climatic conditions, this glacier here is just getting direct snowfall, no avalanching. So that's going to lose a lot of area under the same climate warming conditions. So this scatter has a lot to do with local topography, which is not true, by the way, for larger glaciers. And that's what I wanted to talk about here. You know, if we plot the fractional area change or the percentage change of these glaciers as a function of their original area, you can see all the little glaciers, they're all over the place. There is no trend here. Whereas you come out here in the larger glaciers and things kind of quiet down, and there's a more kind of consistent signal here of glacier change, that it's somewhere around 20%. Well, you know, your first thought is, oh, well, that's probably a sample size problem. If you had a lot more bigger glaciers here, you'd fill this in and be equally noisy. Well, that's a reasonable idea, but all our data everywhere else shows the exact same thing, that the larger glaciers tend to have a more coherent signal, whereas the little glaciers are all over the place. And they're all over the place for the reasons here. You have a lot of topographic variables that the same size glacier, depending on its situation and exposure to the atmosphere, can shrink a lot or shrink less. So that's a little bit of topographic control. And the big glaciers, like the, you know, I don't know how to pronounce this, the Humes Glacier here, that you notice that it has some avalanching from these valley sites, but you can see that the contribution of avalanches would be quite small relative to the total size of this glacier. So in this case, this glacier would be considered a climate sensitive glacier because it's open to the atmosphere. It has very few topographic effects that might change how it gains or loses snow. Whereas these glaciers would be considered kind of climate insensitive because they're highly affected by local topography. And that's just something that I wanted to mention because it kind of confuses the issue of how much glaciers change in any given area. And it depends on a lot of these smaller issues that you might not otherwise consider. So one of the reasons why we chose the Blue Glacier, or well, chose this region, I should say, is that the Blue Glacier has a wealth of information. People have been looking at this glacier for over 100 years. And in the early years, here 1910 to 1930, there weren't any measurements on the glacier as such, but people hiking in the area would take photographs because it's the biggest glacier and it's on the highest peak within the Olympic Mountains. So from these photographs, we can estimate what the area of the glacier is. And you can see here in this figure what the 1919 margin used to look like. The glacier used to be way out here. And by 2009, it had retreated there. And by 2015, it's kind of back here a little bit. So anyway, we're able to work back before instrumental records and before aerial surveys. We can work back what the size of these glaciers, and particularly Blue Glacier, was. So we have a very nice record of glacier change over time. And you can see out of the turn of the last century, the glacier retreated. And then through here during mid-century, mid-20th century, it kind of flattens out and actually begins to advance a little bit. And then it retreats. And then by 2015, it falls off our chart. So it has this roller coaster effect. And this period of time here is actually well known. We see this response in almost all the glaciers in the Western US. This is the mid-century cool period where the climate was a little bit cooler and glaciers had stabilized, and some glaciers like the Blue Glacier here advanced a little bit. So the thing is, what we wanted to do is we wanted to say, well, gee, maybe we can use the Blue Glacier as an index glacier. So maybe the other glacier, the areas of all the other glaciers in the Olympics are correlated with the area of the Blue Glacier. And if that's true, we can then estimate what the area, what the area of the other glaciers were during this whole period of time. And that's what this graph on the right does. It takes the area of Blue Glacier and plots it against the area of the glaciers elsewhere in the Olympic Mountains. And these are the 4 points of those 4 surveys that we conducted. And you can see that it's a straight line. So this gives us confidence that we can use the area of Blue Glacier to extrapolate the area of glaciers throughout the entire Olympic Mountains. So that's this graph here, that's those points there. Then to get a more continuous graph, a continuous data set, I should say, because we wanted to correlate this with climate, we developed a small mass balance model, a very simple one. And I'm not going to go through this a lot, other than just to say the mass of a glacier, the amount of ice and snow in a glacier is based on how much snow accumulates in the winter and how much snow and ice melts off in the summer. So all this model does is the mass accumulating in the winter is equal, the melt, I should say, in the summer is equal to the melt rate times the difference between the air temperature and the melting temperature, or the temperature at which the snow begins to melt. And then for the mass accumulation down here, the amount of snowfall, basically, if the temperature is below -2 centigrade, all the precipitation falls as snow. If it's greater than or warmer than +2, it all falls as rain. And we divide up the difference in between those two temperatures around freezing. So based on this incredibly simple model and using data from a gridded data set, what this is Chris Daly here has taken all the weather observations in the United States, and he interpolated the data between weather stations in order to give monthly temperatures at each location across the United States. And this was gridded into cells of 800 meters on a side. So in other words, it's just kind of a spatially averaging technique using all these weather stations. So using that data, since we don't have any measurements of the entire Olympic region, we use this data here as input to the model. And this is winter precipitation in blue. This is a running average. The real of think about a year. The real measurements here are in the dashed lines, and then we have winter air temperature here in the red, and then summer air temperature up here. So notice one thing here, or there's two things to notice. First of all, there's no trend in the winter precipitation. Yes, it goes up and down, but the beginning and end are about the same. Whereas the winter air temperature apparently begins to rise in the 70s, early 80s here. So the winter air temperature increases, and the summer air temperature kind of slowly increases over time, and then more recently increases. So using this as input to this very simple model, we developed the mass change of the glacier here in the gray. And you can see it has all these little squiggles in it. Now, I'm kind of switching things on you a little bit. The dots are area change, and the grayish line here is mass change. So they're kind of two different things. They're related to each other, but they're kind of two different things. But obviously, they have to be somewhat related, because as the glacier grows in mass, it expands in area, and as it shrinks in mass, it shrinks in area. But the mass is important because changes in area can be affected by a lot of other things. And what you really want is, if you want to correlate it with weather, you really want the mass change. So that's what we kind of did here. Again, this is the same plot I just showed you. These are the area points here. This is our model here in the gray. And up here is the temperature difference. It's no longer the temperature in terms of, oh, it's 4 degrees C. This is the difference in temperature from the long-term mean. So this gives us a way to emphasize how temperature has changed over time. And then the dark plot here, this is precipitation and how that's changed with time. Again, it's a difference. It's the precipitation divided by the long-term mean. So what you see here is that the temperature, like I said in the previous slide, is increasing here, particularly in the last few decades. And the precipitation hasn't changed much at all. Yeah, we have some decades of more or less precipitation, but there's no trend to this, unlike temperature. So this is what's driving the change in the Blue Glacier, and therefore the change in all the other glaciers in the Olympic region. These dashed lines are changes in the PDO, and I'm sure many of you have heard of the PDO, and that's the PDO definition up here in the upper right. This is the Pacific Decadal Oscillation, and basically what it is, it's a way of mapping sea surface temperatures. And the positive phase, this has always kind of confused me a little bit, because you look at the positive phase and your eyes attracted to this big blue cold blob of water. Well, the positive phase is related to the warm water up here against the coast. And the negative phase, or the cool phase, is cooler water up against the coast here. So this has dramatic influence on the glaciers in the Olympic Peninsula, because during warm phases, this is a warm phase here, the glaciers shrink like crazy. And you can see here that the temperatures are a little bit warmer than they were back here. Here's cool temperatures, so-so precipitation, glacier isn't doing much. A little bit warmer temperatures, so-so precipitation, glaciers retreat like crazy. Here's the mid-century cool period. Lot of cool temperatures, a little bit warm, lots of precipitation during these cool phases. Glaciers not only doing okay, but advancing a little bit. And then since that time, deficits in precipitation and lots of warming. So this is the cool phase. This is the cool phase, warm phase, cool phase. And this is supposed to be a warm phase. And then the last one's a cool phase. But because the temperatures are so much warmer, the effect of the PDO switching doesn't really help the glacier, because this is kind of climate warming overtaking the effect of these phase changes between warm and cool periods of the ocean. Another element to this is the direction of the wind flow. And that's what this Pacific North American pattern is whether the wind comes into the US from Alaska, or does it come in more from the Pacific Ocean, and the location of the high pressure system here. And the high pressure system is here. We have a lot warmer temperatures and less precipitation. And then when the high pressure is off in the middle of the ocean a little more, we get a lot more precipitation and cool temperatures. And this is related a lot to freezing levels. And these two climate indices, and again, these are just simple ways of talking about complex patterns in climate. They're both highly related to what's going on with the glaciers. And it's kind of consistent, kind of a consistent story. So here's the deal. Here's one of the big take-home messages from what we've been seeing. This is the same graph I showed you much earlier. This is the average temperature and precipitation, monthly temperature for the Olympics, the Olympic range. And with climate warming, these winter temperatures are increasing, getting closer and closer to the freezing temperature or melting temperature, such that we're getting less snowfall. Same amount of precipitation, more rain, less snowfall. So typically, on a normal, quote unquote, normal climate conditions, wintertime, lots of snow builds up, glacier gets nourished. Summertime, warm temperatures, snow melts off, ice melts off. The two are in equilibrium. The amount of snow you get in the wintertime is more or less equal to the amount of snow and ice melt. In summertime, glaciers are stable. With climate warming, particularly in the Olympics, this doesn't happen as much at higher elevations in the North Cascades or in the Rocky Mountains. But in the Olympics, because they're at lower elevations and the winter climate is warmer, as climate warms, we're getting more rain and less snow, same amount of precipitation. Rain doesn't nourish a glacier. It doesn't add to the ice content. Snow does. And then in the summertime, you're getting warmer air temperatures, so you get even more melt. So the glaciers in the Olympics are suffering from a double whammy. They're getting less snow in the winter, and they're suffering more melt in the summer. So they are receding much faster than glaciers elsewhere because of their low elevation, and that they're so close, the winter temperatures are so close to this freezing level. So our question then is, what happens in the future? Will this continue? And if it does, how long would it take before these glaciers might disappear? So we borrowed a model from Gary Clark, who's a professor up at the University of British Columbia, and his colleagues. And they did this model of all the glaciers in British Columbia and tried to understand what would happen to them in the future. And what this is, it's a global climate model that a lot of the global climate scientists use. And it's used to drive a local glacier model. A local glacier model much more sophisticated than the one I was using. This is a little different because it models the glaciers, all these little glaciers populated across the landscape. Using this model, which is, this is peer-reviewed science, so it has a good foundation. Applying that model to the Olympics, we find that under the regional concentration pathway, which is just how much forcing there is from carbon dioxide and other greenhouse gases. In short, this 8.5 is what we call business as usual. You can see that the area of the glaciers pretty much vanished by around 2070. Your eyes probably attracted these spikes. This model has a funny thing that when the glaciers are widely distributed like they are in the Olympics, the model seems to put an expansive area of snow on the ground that then melts off sometime later in the model period. And it doesn't add much to the volume because you can see here there's hardly any spikes in the volume of the ice. But sticking up to here, ignoring these spikes, you can see that the glaciers, total area of glaciers retreat, and like I said, essentially vanish in about 2070. Under a more mild scenario, the glaciers are larger, but they still also retreat, and they might last to 2100. So either way, with the business as usual, which is what we're doing now, or if we mildly cut back our greenhouse gases, these glaciers are going to disappear either by 2070 or by about 2100. It's only through really ramping back and almost eliminating our greenhouse gas contribution to the atmosphere do these glaciers survive. This bottom plot here is just the volume, and it kind of shows the same story, but in terms of the volume of the glacier. So this is, looks like it kind of flattens out. Business as usual flattens out by 2050, 2060, and probably gone by 2070. And then this more mild scenario kind of disappears vanishes very small amounts in 2080, 2090. So, what this actually means is I don't think the glaciers are going to entirely disappear. That's quite hard to model, because what's going to happen is these glaciers are going to retreat into more and more protected areas, kind of like I showed you in a few slides ago, such that they're kind of protected from the sunlight, They have a lot of avalanching, but they become like the glaciers of Colorado. You know, they're only the size of a house. They're not going to be the size of, you know, several city blocks like we have now. So even though this model predicts glaciers vanishing, they'll just get really small and essentially vanish. And I think this is just a harbinger for what's going to happen to the other glaciers around the country. So in conclusion here, you know, we've had 35 glaciers disappear since the 1980s, and about half of the glacier area has been lost. And unlike glaciers like high on Rainier, for example, that are sensitive to the summer air temperatures alone, because of their low elevation, the glaciers of the Olympic Peninsula are sensitive to both winter and summer temperatures. For the reasons I outlined, that it's the change from snow to rain that doesn't add to the glacier mass, and therefore the glaciers don't get nourished as much. And the fact that the mass change or the change of these glaciers are correlated with these climate indices here, the PDO and PNA, underscores the importance of the effect of the ocean just offshore, which, you know, isn't surprising. I mean, you have this huge Pacific Ocean just outside of the Olympic Peninsula. So of course, ocean conditions and the way the airflow comes off the ocean dramatically affects these glaciers. And that's kind of no surprise. And finally, the sad news is that, you know, if we continue with our carbon dioxide and other greenhouse gas emissions like we have been doing, these glaciers won't be lasting very much longer. I'll be out here before they retreat, but our children probably won't be. So I'll leave it on that depressing note. So thank you.